Okay, let's carry on with the looking at this past paper. Now we're on to question 3, I believe. So let's have a look here. Question 3. See if I can find that. So it's question 2. Discuss the importance of lighting in machine vision applications and identify advantages that can be provided by use of light-emitting diodes. Support your answer with examples. Well, there isn't really any exact way of answering this that I'm particularly wanting you to do. It's really your own style and your own approach, but it'd be good to mention certain things, I think, really, which, of course, lighting is a very, very important aspect of machine vision and often overlooked, especially in books, which tend to often want to give you a bit more maths and some technique rather than talk about this. You might find a lot of useful information, though, in the STEM Image and Vision Handbook, which I mentioned before, which I've given some copies of Gordon to hand out in the reception of the BRL. So you just go there and collect from him. He'll be able to give you a copy of that. And that contains a lot of information about lighting, so it's worth having a look. And what you're trying to do with lighting a lot of the time is identify things of interest to make it as easy as possible to image them and get segment them and get rid of the background. So it might be the top of the box, a simple example. You might have a black background and a bright light on the top of the box, giving you the best chance of measuring the top of the box. I mean, by carefully controlling the lighting, you can simplify the software, you could say, really. So we're trying to separate the feature of interest in the background by as many grey levels as possible, I guess you could say. Another thing you can also do, of course, is use structured light. And that's loads of examples of structured light. And one example is, of course, photometric stereo, because having those 3 or more lights arranged at known locations is, of course, structured light. Another example of structured light is laser triangulation, really, or where you project a pattern onto and then triangulate to work out positions. They're all different ways of structuring light. Now, there are many different types of lighting that provide different functionality in different situations. For example, if you wanted to use a wide range of frequencies, then you might use an incandescent lamp, like a conventional light bulb, because that was being a continuous spectrum from that. It would allow you to use whatever frequencies you want. In general, LEDs are only a bit more specific in terms of the frequencies of light they generate. And it could be you need certain frequencies of light in certain applications. You could use lasers if you really wanted a certain example like that. Another example might be you might need an extended source. So I talked a little bit about when we were doing polished stone. We were polishing stone and looking for little defects on the surface, because any mechanical defects caused by damage to the polishing surface would be not acceptable in the stone. So one way of doing that we found was to shine a light actually using a fluorescent tube, and then use a technique called dark field illumination, or bright field illumination, whereby you look at the reflection. You rig the camera up such that it's looking into looking at the sort of specular or mirror type reflection of that light. And then you see a bright line corresponding to the fluorescent tube. Any little defects, scratches and so on, tend to scatter the light and they appear as little black marks. And that's called bright field illumination. That's very commonly used, especially when you've got minor defects on surfaces like that, and you need an extended source, such as a fluorescent tube, to do that. So let's go on to the next bit of the question. Identify advantages that can be provided by use of light-emitting diodes, LEDs. Well, of course, they're very versatile, and you can turn them on and off quickly, which is quite a big advantage, really. Useful, for example, in photometric stereo, where you want to turn them off very quickly, especially if someone's walking through the photoface rig. You haven't got time for it to be a delay there. If you want a particular frequency of light, they're also useful for that, as I was saying a minute ago. If you're just looking for particular frequencies, you can get LEDs, solid-state devices that will give you that frequency. Another, of course, advantage of them is that they're quite efficient. So they don't generate as much heat as incandescent bulbs, and therefore they don't have all the problems with heat generation like dissipation and overheating that you might have got before, and also, that they don't use as much energy, of course, being more efficient, so that's an advantage as well. Okay, so that's part A. Let's move on to part B, which we got here. Figure 3 is a schematic diagram of a binocular stereo being used to determine the distance Z of a point on a 3D surface. The two cameras are identical and both lenses have focal lengths f of 6 mm and are positioned with their axes at x equals 0 on the camera sensor and the pixel size in each sensor is 10 by 10 microns. Derive an equation Z and calculate Z for a situation where x1 equals -10, x2 equals 4, and d equals 30. So here we've got a setup. Now these are schematic diagrams showing the two cameras. So this is the axis of this camera, and this is the axis of this camera. So when we say here that the axis of x equals 0, we just mean that the position in the array of the pixel array is x equals 0 is where this line is, and also x equals 0 here is where this line is. So we've got to derive an equation to work out z, the distance, in terms of these other parameters. And of course, what you need to do is to have a look at your lecture notes for this course. And if we go to have a look at the one that is relevant to this, we've actually got stereo triangulation. Stereo triangulation and binocular stereo is the same thing, really. So here we have slides on this stereo triangulation: distance, a range of features, determine correspondence. So we've got the similar diagram, we've got the maths, which you should be sort of familiar with, and this is something that's definitely worth revising for this one. And we come up eventually with this equation, just a little bit of geometry, come up with this equation: range in terms of these other parameters, disparity plus disparity. In practice, the measurements in relation to the coordinate frame, so we get this here. Now, focal length, distance between the cameras, position in the feature of interest in the first image, position in the second image. Now, all you really need to do then, I suppose, is to substitute those into this, substitute these values that we got here into that equation I just mentioned. Now, the thing to look out for here really is units, because we've got centimeters, some of them are given in centimeters, some of them are given in millimeters, such as the focal length of the camera. And then we're talking about position here in microns of where these points appear. Now you've got to bear in mind that each pixel has a side length of 10 microns. So you need to make sure that all these units are correct and that you've got it all sorted out accordingly. And this is quite a long distance application in this particular paper, I think, because when I worked this one out, I got 128,571 millimeters, which comes to 128.6 meters. So you show all your work in a course, and you shouldn't have any problems with that. So it's just working out an example of what, how you find out range with binocular stereo. In machine vision, pattern recognition is used to model image data in order to detect the presence of patterns, features of interest. Identify two ways of implementing pattern recognition other than irregularity in neural networks. In each case, explain how it is achieved. Use diagrams to help with your explanations. Now, again, that you don't necessarily have to come up with the ones that I'm going to suggest here, but these are just examples that I thought might be useful. First one I've got is template matching. Now, of course, you did this, I believe, in the machine vision tutorial, and we actually had clips for holding pipes in place, and what you needed there was to work out the a template which was, I think, the hole in the clip, and then you were matching it and trying to measure each clip image to see if all these things are made to the right specification by measuring the position of this hole on this clip. So that's how it works. You have a little small image, and you slide this template image across the original image. As it slides, it compares or matches the template to a portion of the image beneath it, and then you identify where the one is of interest is. Now, another potential one is, you'll find in the lecture notes, is polar signature. With this, you find the center of the feature of interest. That's just a centroid, which is just the average XY position of pixels for the feature of interest. And then you sort of scan around by looking at a line coming from the center outwards and seeing where the outside edge of the feature impinges on the line, as it were, or cuts a line. And then you get a plot of distance, a graph of distance on the y-axis against that angle. And you get like a plot of some kind of function, which is a curve, which is dependent on the on the feature of interest. And I could go back now and look through and show you that, but I think you'll be able to do it yourself. You'll be able to find it in the lecture notes. Polar signature. So two examples I gave were template matching and polar signature. These I don't necessarily go on and ask you about advantages and disadvantages, but they do of course have advantages and disadvantages. One advantage of template matching is fairly simple and standard way to go. It's got a disadvantage perhaps of if a feature is rotated a bit, it may not recognize it. Polar signature, on the other hand, is a little more complicated to work out, perhaps, but it's got the advantage that even if the feature of interest is rotated, it'll still work because it basically just shifts that function describing the shape along the x-axis. That's all that means when it rotates. I think that'll all make sense when you look at those techniques. Make sure you include some figures there. It says include diagrams to help your explanation. So I'll be looking for some, some decent diagrams there to go with that. Now, question 4. In computer vision, neural networks have been a common technique for pattern recognition. Briefly explain what a neural network is and how it functions. Include a diagram to help with your explanations. Say why neural networks are well suited to applications such as image modeling. So, a neural network, of course, as you know, is an information processing method that's inspired by the biological nervous system of the brain. It's a very crude analogy of the brain, I suppose. So the neural network is composed of a large number of highly interconnected processing elements that we call neurons, working in unison to solve specific problems by learning, rather like humans do, of course. In fact, in the early days, the guys who did a lot of work on this was Geoffrey Hinton. He's always been trying to simulate the way the human mind works. That's what he says he's doing with neural networks. And he advised Jan LeCun, who developed the LeNet-5, which is still used now by banks to recognize handwriting on checks. This is where it came from in the early days. So a neural network is configured for a specific application, such as pattern recognition, through a learning process, as I say. Okay. In biological systems, this involves adjustments to the synaptic connections that exist between the neurons in the brain. But this is also, in a crude way, I guess, true of neural networks, where training is used to adjust the weights associated with links between the artificial neurons. And so it says include a diagram to help your explanation. So you want to put a diagram in, such as you'll see in our notes, the notes that I put on the course. And maybe I can just go back and show you quickly what I'm talking about with those notes. Trying to remember where we are. Might be in this lecture. Look here. Yeah, lecture. Got a nice one. So the convolution I talked about earlier, filtering skeleton. Well, there's skeletonization I talked about before. Okay, there we go with pattern recognition. We got with that could be template matching. You could be doing there, but the problem when they rotate. There's the diagram for the polar signature, irregularity we talked about before. So neural networks. So this could be a typical kind of diagram that one might generate for it. So here you have the neurons and the weights between them, and of course, the way the neural network models things is to adjust the weights, which are just multipliers. So a number comes out of here, it's multiplied by this weight, and it goes into here. The transfer function links the input it's got to the output. It's usually non-linear, like tan sigmoid or something like that. If you have a couple of layers, then you're able to, and some non-linear transfer functions, you're able to model non-linearity, which is a big advantage of neural networks. And of course, you can have different numbers of inputs and outputs, and it'll still work. I'm just giving you a bit more background, might be needed for specifically this question, just to give you some interesting background. Things I was talking about in the lectures. This uses feed-forward backpropagation. The simplest kind of neural network works in that way. So you put the value, you have a training set. The data in the training set, has inputs and outputs in it. You look at the inputs, you put them in. It goes through the network. The network's all randomly allocated, all these weights to start with. Comes with an output here. You compare that to the network output to the actual output in the training data. You see an error. That error is used then in a backpropagation procedure where you go backwards to the network, modifying. The network does this iteratively by itself, modifying these weights to see if it can reduce the error. It keeps doing that thousands of times, and then eventually you get a good match. The weights are such, the model is in the weights, and the combination of weights is such that when you put these values in, you get the expected values out. So it's modeling in a sort of statistical way, I suppose you could argue, inputs and outputs. That's a schematic diagram of it. And the question then we got here is, why are neural networks suited to applications such as image modeling? Well, they can model, as I just said a minute ago, a large number of inputs and outputs, and they're very good at modeling nonlinearity, which is what you get a lot of the time, as I talked about in the lectures. Things aren't necessarily linear. Relationships, especially in industry, are often nonlinear. One thing nonlinear affects another. Could be exponential, could be quadratic, it could be some other function, but you don't have to worry about that with a neural network because it's automatically taken care of in the training process because it's data driven. You don't prescribe some formula. It's all taken care of in the training of the network. It's also good, actually, if you've got a lot of noise in the images, which is quite often the case in image processing, to be honest. Or if you've got incomplete data, it still works quite well. Okay, so if we go back to the exam paper, today, convolutional neural networks are very often employed in machine vision research. Give a brief explanation of the meaning of the following CNN terms. Convolutional layer. Well, that's a layer that consists of a set of learnable filters that detect specific features. Activation maps from the filters form the output of the convolutional layer. Okay, so the convolution layer uses convolution, and it's the first layers. It consists of the first layers in a CNN, and it sort of detects different features. It could be detecting a straight line. It could be detecting different filters, detecting curves, detecting different features that are commonly occurring in images, and then it's creating this thing, as I call the feature map or activation map, which is really the output of the first layer of convolution. But basically, it's a way of recognizing this is what's enabling the thing to identify features automatically, because it's seeing, by you applying these basic filters, it's seeing features in the image or identifying that are occurring in the image, and it's using that for training. Okay, so it's a way of that's the way it's working, really. The next one it's asking about is pooling layer. A pooling layer reduces the dimensions of the data by combining the outputs of neuron clusters at one layer into a single neuron in the next layer. Because you can imagine that if you've got these filters instead of just simple neurons, and you've got all this filtering going on, you're generating vast amounts of data to these activation maps. If you carried on doing that, you'd be overrun with loads of data. So you need to try and reduce down the amount of data you've got. So pooling is a way of doing that, pooling layers. There's also another thing called the ReLU layer, actually, which gets rid of negative numbers and just turns them to zero. Fully connected layer. Now, fully connected layers connect every neuron in one layer to every neuron in another layer, as in a traditional multi-layer neural network. And that's used for classification, which is what neural networks are good for. So in a CNN, you've got these convolution layers near the front. Then you've got your pooling layers and ReLU layers to basically pooling to reduce that data down, make it more manageable. And then towards the back, you've got the fully connected layers, which are more similar to a conventional neural network, with fully connected layers. So they're used for classification in the feed-forward backpropagation way I was talking about a minute ago. So that's really the answer to that question. Convolutional neural networks automatically identify characteristics of a dataset that can be used as reliable indicators, such as features. This provides a number of advantages. See what two of these advantages are. Well, the two that immediately come to my mind is that CNNs don't require the user to handcraft features, like we used to have to do before 2012. So the labour involved in pattern recognition is significantly reduced. Supposing I'm looking for dogs, I don't have to start worrying about what I think a typical dog looks like, and then start seeing if I can recognise that feature. That's what handcrafting is. Instead of that, I just set the CNN to work on with a massive number of images of dogs, and it works out itself what dogs look like. Apart from being a lot less work for me, it of course means that you're more likely to get an accurate performance, a reliable performance, because rather than my idea of what a dog looks like, the system's generating it from the data. So that leads on to the second big advantage of deep learning or CNNs, is that the conventional approach has been exceeded in accuracy from almost every data type. This is why you're hearing so much about it all the time. It simply works better than most other techniques. And that's why it's so powerful. Nowadays, you can get face recognition systems using CNNs which are comparable, if not better, than humans, for example. Okay, so that's part C. You may be able to generate some other ideas if I'll be interested if you do, but those are the two that come to mind. Part D, convolutional neural networks have traditionally required large amounts of training data. However, in recent years, techniques have emerged that can reduce the amount of data required. Identify two techniques and give a brief outline of how each works. Well, the first one that comes to mind, of course, is transfer learning. Transfer learning, in a nutshell, is a machine learning technique where a CNN trained with one task is repurposed on a second related task. So you train a neural network, a CNN, convolutional neural network, with a certain amount of data. It could be the ImageNet data set off the internet, which contains so many million images, which are actually annotated, so you know what they are. And then that's a lot of training with that. And then you have a limited amount of data for your particular application, and then you continue training the network with that. You wouldn't think that would work very well, but it works remarkably well. maybe not quite as well as training it from scratch with your own data, but it works pretty well, probably better than other techniques that aren't deep learning, and you don't have a problem with it. I mean, an example of what we did for that, for example, we had a face recognition system that was implemented in convolutional neural network, and that was working fine. But then we started looking at pigs. Now, pigs, to you and I, it's hard to recognize a pig, but to other pigs, they're quite easy to recognize each other, and the information's there. So we found that just by using the CNN we developed for humans, applied it to a limited amount of pig data, we could get pretty good reliability for pig recognition for individual animals. So that was an example of it. And a great benefit, of course, of it is that you don't have to mess around trying to capture vast amounts of data, which is the limiting problem usually. Because the traditional approach with CNNs before these kind of techniques was they needed loads and loads of data. And that is the limit, because small companies haven't got time to capture thousands of images every time they want to do a bit of modeling. But with this, you can get decent performance even with, say, 40 or 50 different images per class, which is pretty amazing. There is another technique which works well, and you're aware of, and it's called data augmentation. That's where you significantly increase the diversity of training data available without actually collecting new data. It employs techniques such as zooming and horizontally flipping the data. So you wouldn't think this would work, but you get a set of data, you mess around with it, zoom in and out, create apparently more data just by doing that, flipping it, and so on, and then you use that for retraining. You find that the performance of the network will often be increased significantly by doing that. So that's data augmentation. So there we have question 4. Let's have a quick look at question 5. An aircraft maintenance company wishes to inspect aircraft surfaces such as wings for damage such as cracks or dents due to bird impacts. This can be achieved using a camera with a relatively small sensor chip in combination with a lens with a short focal length. Alternatively, a camera with a larger sensor and longer focal length lens can be employed. State which of these two options you would recommend and say why. Assume that cost is not an important factor. Well, I've got to admit, I'd recommend a larger sensor with a longer focal length. And the reason is because it's a metrology application. So a longer focal length would mean less lens, like I talked about before, barrel distortion, which would lead to better accuracy. Also, bigger sensor means bigger pixels, more light entering, better quality image, meaning improved performance. So that's the answer to part A, really. Part B, the surfaces mentioned in part 5A are to be inspected in regions of dimensions 23.6 times 23.6 centimeters, assuming that the camera sensor size is 12 by 12 millimeters, and that the lens to be used is a focal length of 14. Calculate the distance above the surface that the camera would need to be located to image a whole region. Show your calculations and include a schematic diagram showing the surface, lens, and camera sensor. Now, of course, you can generate the diagram, it's not a problem. You remember that there was an equation for determining field of view, in fact, in one of the early lectures, and that can be used to calculate the distance above we need to be to image the whole region here. You just need to identify the field of view, sensor size, distance, and focal length. You'll find this in the lecture notes, and it's a standard approach, very simple geometry, which will allow you to work out the distance. And if you enter the distance according to the calculations I've got here, then you're going to end up with a distance d of 275.33 millimeters. So that's the answer to part B. Part C. The aircraft surfaces mentioned above have a matte appearance due to wear and discoloration in places in the bird impacts. The company are considering using photometric stereo to detect any cracks or dents. Explain what photometric stereo is and how it's implemented. Use diagrams to help with your explanations. Say why photometric stereo might be particularly useful in this application. Well, this is a technique, remember photometric stereo, talked about it quite a lot, a technique for generating surface gradient data involving 3 or more lights at known locations, turned on one at a time, and you capture 3 images, and then you combine those images with a lighting model, such as Lambert's law, and to determine the 2D and 3D information for the surface, 2D being like pigment or coloration of the surface, and then 3D being what we call the bump map, which is a dense array of surface normals. Each point on the surface, where you normally have a pixel, is represented by a vector, which just gives you the surface orientation, surface normal vector. So you're getting that gradient information. I want to put a diagram in there. Yeah, there's quite a bit of information. You might find more information off the internet to help you do a bit of revision around the side of this. Why is it particularly useful for this application? Well, the reason is for that unlike just taking a normal image, photometric stereo allows you to isolate and therefore detect the 3D profile of the surface defect in the presence of 2D surface discoloration due to bird impacts. Yeah, so this discoloration could be separated from the actual surface geometry, and then the two inspected separately. You don't want to confuse some muck on the surface that's discoloring it with actual cracks or damage, physical 3D damage. And it's remarkably robust photo exterior in separating the 2D and 3D data. Erosion damage on the wings of an aircraft due to a mechanical influence of the wind and rain leads to an increase of roughness, which can cause reduction in the aircraft's efficiency. Therefore, the company also wishes to detect the amount of surface roughness at various points on the aircraft by measuring surface irregularity with a camera of high resolution, for example, less than 10 microns. Explain why photo exterior will be useful here and say how you would expect the field of view of the roughness measurement system to differ from that of the inspection area system. Well, I suppose you guys can think about that. You've got to think about the field of view here, really. If you're looking at the roughness, and it says there 10 microns, you're really going to need to look at a much smaller area than if you were looking at a much bigger area. As it says here, the irregularities are only around 10 microns. Much smaller than the dents which you might expect to see in the aircraft. Therefore, a much smaller field of view will be needed. The other question of why film exterior will be useful, well, we already covered that one, really, haven't we? You can reliably and quickly at high resolution separate the 3D roughness information from the 2D discoloration. The 3D roughness information is what you need to do. You're covering that 3D information, and that's what photometric stereo is particularly good at. It's very good at giving you high resolution texture recovery, and that's what you need here. You've got the surface orientation changing due to roughness, due to the wind and rain, and you want to measure that on a small scale, even when you've got discoloration. Okay, that's what, and photometric stereo will allow you to do that. The company have confirmed they intend to employ photometric stereo to measure the irregularity on the front of the wings, but are concerned about depth of field issues. Explain what they mean by this and how depth of field may be influenced by sensor resolution and lens aperture. Well, depth of field is a measure of what range of distance from a lens remains in focus in the image. You may have seen this in photography books. If you've got, say, a railing coming towards you, if you've got a small depth of field, you only focus on a bit of it. You can't focus on all of it. But in order to measure 10 micron features, a relatively high magnification would be needed, which means a smaller depth of field. Since they wish to measure the curved front of the wing, some parts of the surface in the image will be closer than others, so they're concerned about the image being out of focus. Okay, that's the answer to that next bit, really. How depth of field may be influenced by the sensor resolution and the lens aperture. What about a higher resolution sensor? Well, I think that would increase the depth of field, because a high resolution sensor would increase it because you could get away with lower magnification in the optics, but still get the same resolution in terms of resolving on the surface. So a high resolution sensor could be a way forward on that. And of course, talking about, I mentioned about photography, SLRs and conventional photography. One way they illustrate in books often about how they increase the depth of field would be to reduce the aperture down. If you've played around with cameras, you'd know this, that when you reduce the aperture, you get a bigger depth of field. So that's another thing you could do, to simply decrease the aperture. So those are the answers to the questions, and I hope that's proved useful. I'm not saying that the answers everything I'm saying is exactly all that could ever be said in response to these questions. I'm just giving you what comes to mind as sort of model of some sort of fairly decent answers from my point of view. So all the best with the exam, and I hope that's useful. I'm sure you guys, because every year I'm pretty impressed with what people do on this course. So I'm expecting some good answers, and I'll be marking them as soon as they come through. So all the best, and take care, and I'll see you again.